Right now, a machine, about the size of a compact car, is moving through a region of space that has never once fully matched the models built to describe it. It runs on roughly 4 watts of power. The small bulb inside a household refrigerator uses more electricity than that. It was built before the personal computer existed, using switches and memory chips that modern engineers study the way historians study an old manuscript. It was only ever supposed to work for about 5 years. Instead, it kept going. In 2012, it crossed a boundary no human-made object had ever crossed, and its instruments immediately began recording numbers that did not match a single prediction built by physicists in the decades before it got there. In 2023, this same machine nearly went silent for good, and the team trying to save it had to solve the problem from 15 billion miles away, with every question taking almost 2 full days to get an answer. And right now, in 2026, it is losing power fast enough that NASA engineers are testing an experimental fix nicknamed after the biggest event in the history of the universe. This is the story of Voyager 1, and some of what it just told us is still being worked out. You're watching Beyond the Signal, where we follow the evidence to the edge of what science knows. If you like this kind of patient, evidence-led look at real space science, subscribing is a quick way to make sure the next one finds you. There's no need for a dramatic music sting here. The story does that on its own. To understand why a spacecraft built in the 1970s is still rewriting textbooks in 2026, we need to go back to a much quieter moment, one where nobody expected any of this. Not the boundary, not the near silence, and not the fact that this aging machine would still be the single most important source of data about the space between stars. On the 5th of September 1977, a rocket lifted off from Kennedy Space Center in Florida, carrying a spacecraft called Voyager 1. The plan was modest. Fly past Jupiter, fly past Saturn, take pictures, gather measurements, and then drift into silence. NASA expected to close the book on this mission sometime around 1981. Nobody involved expected a headline in 2026. What happened instead turned into one of the most productive accidents in the history of space exploration. Voyager 1 reached Jupiter in March of 1979, returning the first close-up images of that planet human eyes had ever seen. It reached Saturn in November of 1980, using the planet's gravity like a slingshot to pick up even more speed. By the end of the 1980s, it had already traveled farther than any object humans had ever built, and it was still working, still calling home. None of that was guaranteed. Voyager 1's flybys of Jupiter and Saturn worked because the outer planets briefly lined up in a way that happens roughly once every 176 years, letting the spacecraft borrow a little momentum from each giant planet on its way past, like a slingshot swinging faster with every rock. The instruments doing the work were built with less onboard memory than a single modern text message. Nobody involved in 1977 was designing for a machine that would still be sending data home half a century later. They were designing for a 4-year trip. For decades, physicists built careful models predicting what interstellar space should look like in case a spacecraft ever actually reached it. Nearly all of those models agreed on one thing: it should be quiet. Then, in August of 2012, 35 years after launch, Voyager 1 crossed the heliopause, the boundary where the sun's influence finally gives way to the space between stars. Here's the simple version. The sun does not just give us light and heat. It constantly pushes out a stream of charged particles called the solar wind, and that wind inflates a kind of bubble around the whole solar system, one that contains every planet, moon, and living thing we know of. The outer edge of that bubble, the point where the solar wind runs out of push and interstellar space presses back, is the heliopause. Cross it, and you are no longer inside anything the sun controls. In 2012, Voyager 1 crossed that line and kept transmitting. For the first time in human history, we had a working instrument sitting inside the plasma between star systems, a place no telescope on Earth had ever been able to see from the inside. And what it found there did not match the plan. The models had described interstellar space as a kind of cosmic waiting room, thin, cold, and mostly still. Voyager 1 arrived at that waiting room and found something closer to a storm. Starting around 2017, the plasma wave instrument on board began picking up something researchers had not expected and could not immediately explain: a steady, narrowband hum in the plasma around the spacecraft. Not a single spike that could be waved away as noise, but a signal that kept showing up, year after year, across a stretch of interstellar space hundreds of millions of miles wide. Put that in perspective. The distance between the Earth and the Sun is about 93 million miles. This hum has been tracked across many times that distance. When the team studying the data published their findings in the peer-reviewed journal Nature Astronomy, their conclusion was direct. Interstellar space is not the smooth, uniform void the models described. It has structure at nearly every scale, from meters to millions of miles. Researchers still disagree on the exact cause. It may be plasma oscillating naturally in response to nearby disturbances, which would fit inside existing theory. Or it may point to a different mechanism entirely, one that would force parts of the current model of interstellar space to be revised. That question is still open, and no one is pretending otherwise. Here's why this particular signal is different from anything scientists had before. Before Voyager 1 started picking up this steady hum, researchers could only catch isolated snapshots of interstellar plasma, usually triggered by a specific event, like a shock wave from a solar eruption finally rippling out to the heliopause years after the sun produced it. Useful, but scattered. A little like trying to describe the weather across an entire continent by checking a single thermometer once a year in one city. What this persistent signal offers instead is closer to a continuous feed, a running record of interstellar plasma as the spacecraft drifts through it day after day. And that continuous record is what let researchers notice the structure was there at all. Here's why that matters beyond curiosity. The heliopause is not just a line on a diagram. It acts as a shield, deflecting much of the high-energy radiation that streams in from stars that exploded elsewhere in the galaxy, radiation that would otherwise reach the inner solar system, including Earth, at far greater strength. If the environment pressing against that shield from the outside is more energetic and more turbulent than any model accounted for, then the long-term behavior of that shield is a fair question to ask again. Nobody studying this is claiming an imminent danger. What they are saying is that a boundary we assumed was well understood turned out to be more complicated the moment we finally had an instrument sitting inside it. But the plasma hum was only the first surprise. The bigger one showed up in the magnetic field data. For decades, one of the most confident predictions about the heliopause was that crossing it would mean crossing into a completely separate magnetic environment. The sun's field on one side, the galaxy's own field, pointed in a different direction, on the other. Two distinct systems, cleanly divided at the border. That is not what the instruments found. On both sides of the heliopause, the magnetic field pointed in almost the same direction, with far less of a shift than the models predicted. At first, some researchers wondered if this was a coincidence tied to one location. But continued data from the same region and later confirmation from Voyager 1's twin, Voyager 2, at a completely different point along the boundary, showed the same pattern. The sun's magnetic field and the interstellar magnetic field beyond our solar system are, in a way researchers are still working out, connected. Many physicists point to a process called magnetic reconnection, where field lines from different sources meet, break apart, and reconnect, releasing energy as they do. That process appears to be heating this boundary region to genuinely extreme levels. Some researchers have informally nicknamed the area the Wall of Fire. It is not a technical term, and there is no actual flame involved, but the label points at something real. Instruments have measured temperatures in the tens of thousands of degrees Celsius in this thin transitional layer, generated not by combustion but by charged particles slamming into one another as two magnetic environments collide. Put plainly, the border between our solar system and the wider galaxy is not the smooth handoff scientists expected. It is an active, energetic, only partly understood frontier, one where our home star system is exchanging energy with everything beyond it in ways no pre-Voyager model predicted. This is not a footnote. If the relationship between the solar system and the interstellar environment around it is more dynamic than we assumed, then some of what we think we know about how the heliosphere behaves and protects us over long timescales deserves a second look. It also changes what future missions need to look for. Any spacecraft designed to study this boundary going forward will need instruments built to catch fast, energetic activity, not just the slow, gradual transition earlier designs assumed. That is a direct, practical consequence of two aging probes doing something no computer simulation could, actually being there. Before we get to what is happening to Voyager 1 right now, in 2026, there's a chapter from 2023 that shows just how fragile this entire mission has become, and how far a small team of engineers were willing to go to keep it alive. On the 14th of November, 2023, Voyager 1 started transmitting a stream of unreadable data. The carrier signal was fine. The spacecraft was clearly receiving commands and behaving normally. But whatever it was trying to say had turned into a repeating pattern that made no sense to the instruments used to decode it. Nothing quite like it had happened in over 4 decades of operation. By March of 2024, engineers at NASA's Jet Propulsion Laboratory had traced the problem to a single memory chip inside one of Voyager 1's 3 onboard computers, a system called the Flight Data Subsystem. That chip held a small section of the subsystem's own software, the part responsible for packaging science and engineering data before sending it home. It had simply stopped working. In an ordinary situation, you replace a failed part. Here, that part sat more than 15 billion miles away, on a machine with no manual override and no way for a human hand to ever touch it again. The only tool available was a radio signal, and even that took roughly 22 and a half hours to arrive, with another 22 and a half hours needed for any reply. Every single test of an idea meant a wait of nearly 2 full days before the team even knew if their guess was right. And every command carried the same quiet risk. Send the wrong instruction to a computer that old, that far away, with no way to walk it back, and the mission could end permanently, mid-sentence, with no one ever fully sure why. The fix could not repair the chip, so the engineers worked around it. The affected code was split into smaller pieces and tucked into scraps of free memory scattered elsewhere in the computer, including space freed up by deleting decades-old software Voyager 1 no longer needed from its planetary flybys. Each piece had to be rewritten to function correctly from its new address, and the whole patchwork had to operate as if nothing had changed. On the 18th of April, 2024, the team sent the first piece of that fix across the void. On April 20, engineering data started coming back clean and readable for the first time in 5 months, with science data following in the weeks after. A team working from documentation written for hardware that predates most of their careers had performed something close to remote surgery. On a computer built in the 1970s, from a distance no repair crew could ever close. So why does this matter now? Because it shows exactly how thin the margin for error has become, right as that margin is about to get thinner still. Voyager 1 gets its electricity from 3 radioisotope thermoelectric generators, devices that convert the heat of slowly decaying plutonium into usable power. At launch, those 3 generators produced about 470 watts combined. Nearly 49 years later, that number has fallen by more than half. The spacecraft loses roughly 4 watts every year, a decline nobody can stop and nobody can repair. On the 27th of February, 2026, during a routine maneuver, Voyager 1's power levels dropped further than engineers expected, close enough to tripping the spacecraft's automatic undervoltage protection, a safety system that would shut things down on its own and force a slow, risky recovery from the ground. To pull the spacecraft back from that edge, NASA's team made a hard call. On the 17th of April, 2026, they sent a command, one that took about 23 hours just to arrive, to permanently shut down one of Voyager 1's last 3 working instruments. The low-energy charged particles experiment, which had been measuring ions, electrons, and cosmic rays, almost without interruption since 1977. It joined the cosmic ray subsystem, switched off the year before. On the growing list of instruments this mission has had to sacrifice. Of the 10 instrument packages Voyager 1 launched with, only 2 are still running today, one that listens to plasma waves and one that measures magnetic fields. The mission team settled on the order for these shutdowns years in advance, weighing which instruments still had the most to teach against which ones the power budget could least afford to keep running. There is no reversing a decision like that. Once an instrument goes dark to save a few watts of power, there is no future budget generous enough to switch it back on out of regret. Every shutdown is a small, permanent narrowing of what this mission can still tell us. Here's the part most headlines miss. The team has not given up on buying back some of that lost capability. NASA engineers are currently testing a power-saving strategy nicknamed the Big Bang, a coordinated effort to shut down some components and swap others for lower power alternatives, all at once, in hopes of freeing up enough electricity to keep the spacecraft warm and, potentially, switch that shutdown instrument back on. The riskier version of the plan was tested first on Voyager 2 in May and June of 2026, since it sits closer to Earth and has a little more power to spare. If that test held up, NASA planned to attempt the same fix on Voyager 1 no earlier than July, a plan that is unfolding right around the time this story is being told. Nobody on the team is promising it will work. But with this mission, betting against it has a poor track record, and there is one more milestone already locked onto the calendar, independent of whether any of these fixes succeed. On the 18th of November, 2026, at 2:16 and 7 seconds in the morning, Pacific time, Voyager 1 will reach a distance of exactly 1 light day from Earth, about 16.1 billion miles. At that distance, a command sent from Mission Control takes a full 24 hours just to arrive, with another 24 hours before any reply gets home. Send an instruction on a Monday morning, and you won't know whether Voyager 1 received it until Tuesday morning, and you won't hear back until Wednesday. No human-made object has ever operated at that kind of distance before. Voyager 1 will cross that threshold while it is still alive, still transmitting, and still moving outward at roughly 38,000 miles an hour, a speed that adds tens of thousands of miles to the gap with every hour that passes. Bolted to the body of this aging, fading machine is something that is not fading at all. The Voyager Golden Record is a gold-plated copper disc, carrying greetings recorded in 55 human languages, the sound of rain, the sound of ocean waves, the sound of human laughter, and 90 minutes of music drawn from cultures across recorded history. It carries simple diagrams explaining our mathematics and physics, and a map built from the positions of pulsars meant to show whoever eventually finds it exactly where, in this galaxy, to look for us. Carl Sagan, who helped assemble the record, once called it a message in a bottle cast into the cosmic ocean. That description has only become more accurate with time. Long after Voyager 1 sends its last signal home, likely sometime in the 2030s, if current estimates hold, the spacecraft itself will keep moving. There's nothing in interstellar space to slow it down. No friction, no atmosphere, nothing strong enough to meaningfully pull it off course. It will keep traveling in nearly a straight line, carrying that record through the dark, long after every trace of the civilization that built it has changed beyond recognition here on Earth. That is the part of this story that is easy to lose in the middle of the physics. Right now, in 2026, the only continuously operating scientific instrument our species has ever placed in the space between stars is a machine pushing 49 years old, running on less power than the bulb above a kitchen stove, and it is still teaching us things no ground-based model ever could. Not because it was the biggest or the most advanced thing we ever built, but because it was the one thing that kept going long enough to actually arrive. We have since built far larger telescopes, far more powerful computers, and far more expensive missions. None of them have told us what this small, aging, underpowered machine is telling us right now, simply because none of them ever left. There are questions about the space between stars that can only be answered from inside it, not from an observatory on a mountaintop and not from a telescope in Earth orbit. For the moment, we have exactly one working instrument out there to ask. So where does that leave us? What we know is this. Voyager 1 has shown that interstellar space is not the calm, uniform void older models assumed, and it has revealed a magnetic connection between our solar system and the galaxy that nobody predicted. It nearly went silent in 2023 and was brought back by engineers, solving problems across a gap of nearly 2 days per exchange. And right now, its power is fading fast enough that a team at NASA is testing an experimental fix just to keep 2 aging instruments alive a little longer. What we do not yet know matters just as much. Researchers still cannot say for certain what mechanism produces that persistent plasma hum. No mission currently exists, or is funded, to send a dedicated instrument back out to interstellar space to help settle that question. If Voyager 1 goes quiet before one is built, this real-time window into the space between stars closes, possibly for decades. For now, the signal is still coming, stretched across billions of miles, arriving nearly a full day late, describing a region of the universe that is stranger and more connected than any model built entirely from Earth ever managed to predict. If this is the kind of story you want more of, subscribing costs nothing, and it helps deep dives like this one find you before they disappear into the feed. Tell us in the comments which detail here surprised you the most. This is Beyond the Signal. Keep looking past the obvious.